All right, we're back, and not for a math video, actually. So today, what I wanted to start with was some basic pre-circuits knowledge or fundamentals. Just because if I make some circuit videos, I would like to have this stuff as reference so that I don't have to re-explain super in depth. So I think what I want to talk about are voltage and current, and then I believe just Ohm's law, and then we should be somewhat set for moving on to then doing some circuit analysis stuff. So let's begin. So first, let's talk about voltage and current. So voltage and current are both defined in most introductory circuits textbooks as the following. So we'll say for the voltage V, that is equal to dW dQ, where W is work / energy and Q is charge. So what this is saying, and now dW and dQ being the, let's say in pink, this is the first derivative of the work derivative. Okay, let's spell that correctly. Derivative of the not the voltage, of the work with respect to current, with respect to charge. I'm all over the place. So for every charge, what change in work are we getting? So it's just really being, I'm giving this much energy, this much work per charge. And that's what voltage is. How much energy am I able to work with, dependent on the amount of charge that I have in my system. Okay, so that's nice. And then we have current, we'll say is I, and that's equal to dQ dt, where, right, Q is still charge and T is time. So this is just saying how much charge do I have per time. And that's, if I have electrons, right? So an electron, let's draw here, which is like a negatively charged particle. So if I have, and in general you have billions upon billions of these electrons, how much of these charges do I have flowing through my system per unit time, right? And then let me put some labels, some units on here. So voltage, its units are in volts, conveniently enough. And then current, its units are in amperes. Okay. So again, voltage being the amount of energy that we have per unit charge, and current being the charge that we have per unit time. And those are useful because we can talk about the amount of energy in our system and where that energy is moving dynamically being over time, where is my charge, where is my energy going. And these are the fundamental things when we use to characterize electrical systems like devices and circuits, larger complex systems in general. So those are some fundamental things, because whenever we're going to look at a circuit, we're going to want to find voltages and currents. And I guess actually, so I do want to talk about one other thing related to voltage and current, and that would be power. So if we take our definitions of voltage and current, let's actually combine those and multiply them together right here, and we'll see what happens. So if I take voltage times current, what's that going to equal? Well, let's look at the differential forms, these two derivatives that they're defined as. So voltage being dWbq, the change in work over the change in charge, and then current, which is dq dt, right, the change in current over the change in time. And we have two cancellations here. We have charge in this fraction's denominator canceling with current's numerator, which is also dq. And so all we're left with is dw, the change in work, over dt, the change in time. And, right, if we look at the units of this, if we look at the units, what color? I guess I'll do pink. So the units of this would be in change in work would be joules per time, which is second. And joules per second, energy per time, is power. So how much energy are we delivering to the system per second is power. So when we talk about the power of a system, that is purely dependent. I don't know why I started with a V. If we're talking about the power, that is purely dependent on the voltage and the current. So we'll say that the power P is equal to voltage times current. And this is extremely useful. So when we find the voltages and currents in our system, then we can describe the power of that system. Okay. And then there's another thing that we can use to link voltage and current directly, other than power. So a scientist in Germany, or from Germany, Georg Ohm, did some experiments and found if you had a resistive element, which is described here, this is a resistor with some resistance R, and normally this could be some wire that might be wound really tightly around an insulating core, and wire itself has resistance, being the charges that flow through it are being slowed down in some way. They have trouble flowing through as quickly as before, so that's just some type of resistance. And if whenever he applied a voltage, so we'll use, I guess, positive. Actually, let's use green. So he applied a voltage across V, where it's plus here and minus here, and he noticed that he had a resulting current. He had a current flowing into, right here, and as he varied that voltage, he would then see changes in that current, right? And so if we had some mock data here where you had voltage and current, maybe he applied 1 volt and got 2 amps. He measured that, and then say he applied 2 volts instead, and then measured 4 amps flowing through that resistor, and then 3 volts, and then he got 6. So then if we took the time and plotted this, if we plotted the current voltage characteristics of this resistor, you would have, your current here, and then your voltage here. And then if I put 1, 2, 3, if I put some labels on this graph, so that's 1, 2, and 3 volts, and this goes up to 6 amperes. And let me finish labeling that. So then you plot this data that he found for this specific resistor. You had 1 and 2 right here, you had 2 and 4, and then you had 3 and 6. And then you connect here, you find that you get a straight line. Straight line. And then whenever you see this, this is saying that if you ever have a linear line resulting from your data, that means that your variables are directly proportional to each other. So then once you see this, you can draw this conclusion that voltage is directly proportional to current, where this is the symbol for proportional. So this is a precursor to saying something is equal to. You can say, well, they're directly proportional to each other, and you'll say that like this. And what this means, you can rewrite this in something that is more mathematically familiar. You can say instead, right, voltage is equal to some value, some scaling factor times current. So if I have some current, but I know the scaling factor, then I should be able to figure out whatever that voltage, that resulting voltage is in my system. And Georg Ohm was saying that this scaling factor is actually resistance. And so this is the beginnings, or this is where we get Ohm's law from, where V is equal to IR. And R being the constant of proportionality for the proportionality that voltage is proportional to current. And so if you look at this line then, right, this is something that we can find. If you look at this line, well, this is reminiscent of y is equal to mx plus b, right? You'll learn this in an algebra class. And this is the general equation for a line. And we don't necessarily need b, that could be 0. But you'll have your dependent variable equal to your independent variable times a constant of proportionality m, where m is your slope, right? And so in this case, our variable v is equal to IR. Now, this isn't necessarily what we have here. We have I versus V, but that's okay. We can rearrange this. Let's use the purple, using all these different colors today. So if I rearrange this, I can divide by R on the other side. So I equal to 1 over R times V, right? Where I would have to just divide R to the other side. And so if the current is our dependent variable on the y-axis and voltage is our independent variable on the x-axis, then our slope comes from this constant of proportionality here, 1 over R. So then the slope of this line is 1 over the resistance. And this also has a definition. This is the conductance, which we would label as G. That's just canonically they call this G. Okay, but we can talk a little bit more about resistance now. So from Ohm's law, V is equal to IR. So let's unpack this a little bit. Let's redraw our picture now that I got a little bit off the rails here. So we draw our picture. We have our resistance element, okay, and then we have a positive voltage starting across it, and we see that we have a resulting current flowing through our resistance, okay. And then we have said Ohm's law is V, the voltage, is equal to I times R. So this is related to this picture here directly. And notice the signs on our voltage and the direction that the current is flowing. So current can flow in two directions in our like one-dimensional line system right here. So it can flow into the resistor, or it can flow out of the resistor if you're looking at specifically this node right here. So if you have a voltage positive to negative across your resistor, then by what is called the passive sign convention, if you have a voltage from positive to negative, your current is flowing into the positive terminal of your resistance element. And vice versa, if you had a current flowing into your resistance element, you would find then a voltage drop from positive to negative, where the positive terminal is going into your current. Right, and that's just from Ohm's law. So if it was the other way around, we could make this distinction. If this was the other way around, where you instead have a resistance, or a current flowing out. I keep forgetting to draw the R for the resistance. If you have a current flowing out, but you still want to show that you have a positive voltage here, the change you would have to make to Ohm's law, it wouldn't be V is equal to IR, but V is equal to negative IR. So in different problems, you might be tasked to find a specific current going through a resistor. If you find the voltage there, this could result in giving you either a negative or positive current, where your positive current is flowing into the positive terminal and your negative current is flowing out of the positive terminal. Or you could equivalently say that this current is still going through here and it's flowing into the negative terminal, right? So as an example, if you had a voltage source, let's see this in yellow. So if you had a voltage source, let's say we have a 5-volt source, and that is connected across a resistor of, let's say, value 10 ohms. Oh yeah, I didn't even say the units. So voltage in terms of volts, current in terms of amperes, resistance R, that has units of ohms. And that's directly from our scientist Georg Ohm. The unit of resistance is named after him. So, okay. So from this problem, what we want to find is the current flowing through this resistor. So from Ohm's law, right, we know, okay, well, if I have a current flowing directly into my resistor, right, I should be seeing a positive voltage drop from positive to negative across this with a voltage V. Noticing, right, well, if I have this 5 volts across this resistor, that's the same voltage here, right? Positive is still connected to positive here, and the negative is connected to negative. So our voltage V is equal to 5 volts. And from Ohm's law then, right, this voltage V is also equal to I times R. Okay, so then I can set 5 equal to I times R, right? And then the resistance value is 10. So then 5 is equal to I times 10. And then all I have to do to solve for my current now is divide by 10 on both sides. So then let's get a different color, divide by 10, divide by 10. And then we get finally that current I is equal to 5 over 10, which is equal to 0.5, and our units here are amperes. So then that is a problem where we can find the current from a voltage source being applied to our resistor. And then similarly, right, we can have another circuit where, say I have a current source, let's say of 2 amps, and I'm sending that 2 amps into a resistance. Let's say that that resistance is also 10 ohms. Okay, so then from our Ohm's law picture, okay, well, I have this current which is coming through here and flowing. I have 2 amps flowing into my 10 ohm resistor. And what I want to do is figure out, well, what is the voltage V across? Okay, well, I know if I have a current flowing into my resistance value, then the positive terminal of the voltage must be where the positive terminal is placed, and consequently the negative terminal on the other side. So the voltage V is already set up in accordance to the picture of Ohm's law. So then I should be able to find my voltage, right? So let's write down Ohm's law first, right? V is equal to IR. So it's always useful to write down the formula when approaching a problem. And then I just want to figure out what the current is. And the picture is already good, so then I can start plugging in my values, right? So I don't know voltage, that's what I want to find, so then we'll keep that as that. The current is 2, so I can have 2 times the resistance, which is 10. Therefore, I must have a voltage of 20 units volts across this resistor. And so now these are stripped down problems of just a singular source into our resistance element, but these same principles will follow through into more complex circuits, and we'll be able to figure out how our work is being applied to our charges in our circuit, and also where those charges are flowing when we can use Ohm's law to find both the voltages and the currents in our circuits. And I'll just end showing again that V is equal to IR. That is one of the topics that we talked about today, and also the definitions of voltage and power. So now that we have these baseline skills, we can use these when moving on to dealing with and analyzing slightly more complex circuits.